This was not meant, none of these are meant to be difficult, but if you keep up with this stuff and you're awake, and you got enough sleep and stuff like this, they're just meant to confirm what I suspect, that everybody's doing the work. Don't get caught in that trap of cramming the night before. Warn you, or right before, it's even worse. You're gonna hurt yourself, in my opinion. All right, for this one, we have two regions, 1 and 2. I think region 1 is air, is that right? Yeah. And this region has some values, and I did make a mistake, but I walked around, made sure everybody had the right conductivity. For this region 2, we have mu relative equals 1,000, and we have sigma, and this is actually for steel, 1045 steel, and this was equal to 5.7 times 10 to the 6th. And the units are Siemens per meter, 1/0 meters, and epsilon relative, I believe, was 1 of this. Do y'all agree with this?
It's 5.8.
Pardon me?
5.8.
For what?
Sigma.
Or I'm sorry, 5.8. Sorry, thank you. 5.8 times 10 to the 6th. Now, by the way, what this is a common substance, as I understand it, commonly encountered. It's SAE 1045 steel. Now, the reason I know that, in my electromagnetic compatibility course, this is one of the things they mention as a commonly encountered values for metal. Steel is very common. There's different brands of it, but steel is something that you can be fooled about as far as its effectiveness in terms of attenuating signals. You'd think copper would be better, but see this mu relative? It's extremely high. So that will play a big role. Okay. So first we need for these two regions to get eta. And in region 1, this is simply eta naught. And eta naught is equal to 120 pi ohms, or about 377 ohms. Do you all agree with that, class? For the second one, now, if you looked at that, there's a frequency, isn't there?
Yes.
And what is the frequency?
Speed of light.
300 megahertz.
No, not velocity, the frequency. What?
300 megahertz.
Oh. You're right. It's the same as C, but for a reason landed in is 1 meter there, right? Okay. So we've got that frequency. Now we need eta in region 2. So that's the square root of J omega. And how about I just write down omega is 2 pi f and leave it at that. I think everybody knows that, correct? J omega, then mu naught, and mu naught, somebody asked me to put these up here, is 4 pi times 10 to the minus 7. And the units are henries per meter, and then it's times mu relative. Well, mu relative is 1,000. Then it's over sigma steel, plus J omega epsilon relative epsilon naught. Now, epsilon naught is equal to about 8.854 times 10 to the minus 12 farads per meter. This is a very good conductor, by the way. I mean, epsilon relative, epsilon naught omega is orders and orders of magnitude less than sigma. Do you all agree with that? So this is about equal to really the square root of J omega mu naught mu relative over sigma steel. You could do it either way. And what do you get for the magnitude? The angle is 45 degrees, right?
Yeah.
But what's the magnitude?
0.639.
Anybody confirm that? It's going to be about that. I don't have the answers up, but the solutions are up there. I'll use MathCAD for the solutions. Listen, I'm going to level with you guys. I've worked with a lot of different tools, but to get quick, efficient answers for calculations that aren't major undertakings, like where you need matrix stuff and you have to do parallel processing, MathCAD is a dream. Does anybody in here use it? Probably not. I use it all the time for stuff because it's so quick and it's what you see is what you get. I change one thing. If I've got a whole bunch of forms, they all change at once. I don't have to recompile or rerun or anything like that. Okay, now the next thing we need, let's see. Let's get the reflection coefficient and the transmission coefficient. Reflection coefficient is eta 2 minus eta 1 over eta 2 plus eta 1. We may not need this. And transmission coefficient is 2 times eta 2 over eta 2 plus eta 1. Why don't we get, do I ask for the reflected field? I think. No? Okay, let's just get the transmission coefficient. First, let me slow down a little. Does everybody understand what I'm doing and why I'm doing it?
So why do you favor the transmission coefficient?
All right, this value, if you get it and your calculator is rounded off, it might be very close to 1. You add that, all right, minus 1, pardon.
Yeah.
That plus 1 is going to give you an error here because it won't have the significant digit, the level of significance. Do y'all follow me? It can all round it to 0 or when it's not. Y'all follow me? So give me this one. It's going to have an angle about 45 degrees. It's approximately just 2 eta 2 over eta 1, where eta 1 is eta naught. Y'all follow me, class? Can you give me that, anyone?
So one is 0.0024 plus j of the same thing.
How about magnitude?
Oh, I'm sorry. That one is 0.00338 at 45. 338.
At 45 degrees.
Yeah.
Okay. So that's what I really need. Okay. Now after that, I give you a transmitted field through this shield, right?
Yes.
Okay. So and unfortunately, I wrote this stuff down on top of here, but let me just do it right here. I've got a shield. The thickness is 1 micron. The thickness is 10 to the minus 6 meters. Do y'all follow me on that? Is it micron class? Or 2 microns, sorry. 2 microns, my bad. I'm sorry. Y'all with me? Here's what the shield is. I'll call it eta shield, which is really my eta 2. There's some incident electric field here. It's coming in. It's normally incident. There's going to be a reflected field that we, I guess, don't need. I don't need it. There's going to be a transmitted field here. I'll call it E transmitted 1 just on the inside. Then there's going to be a field that gets through the whole thing, and I'll call this, E transmitted 1. This is the actual transmitted field through the entire region, which I'm calling E transmitted 2. Can you follow my ideas about this, class? Just take a moment and gather yourself. Make sure everybody follows me on this. This wasn't meant to be tough, but some people really dropped the ball on it. I'm not sure exactly what went wrong, but I've got to make sure you understand this. You all with me? All right, now, I gave you this, right? Didn't I?
Yes.
All right, what's the magnitude of the transmitted field?
3.579 times 10 to the negative 4.
And that's volts per meter. Now we're going to reverse engineer and get the incident field from that, right here, E naught 0. Do y'all follow me? And let me get over here. By the way, is it going to rain today around 4 o'clock? I'm sorry I'm asking these kind of crazy questions, but in the back of my mind, I have about 3 things to do. One of them has to do with the outside.
No, it's supposed to be sunny.
So somebody said it was going to rain. And I didn't bother looking up. So what is the transmitted field going to be in magnitude? And the way I say to get it is take the incident field. Please watch this. I just care about magnitude. Then I'm going to tell you this. Focus on magnitude with all these, because I don't really care about phase at this point. You all with me, class? And this is, we should get the skin depth. Right off the bat, what is the skin depth in the shield? It's 1 over the square root of pi f mu sigma, or it's 1 over alpha. Might as well get alpha in the shield as well. So this is equal to the square root of j omega mu times sigma plus j omega epsilon, right? Sorry, I'm cramped, which is equal to alpha plus j beta. We won't need beta for this one. In either case, this is equal to 1 over alpha, by the way. I'm a good conductor. Correct, class? Take a moment. I'm sorry if I'm going too quick. You all with me? Bradley, do you understand this right?
Yeah, I already looked at it. Yeah.
Okay, now, for this one, what is alpha plus j beta? Now you can give me the real and imaginary.
I just calculated alpha, but yeah, I got 2.62 e to the 6.
2.62
E to the, or times 10 to the 6.
times 10 to the 6th, all right? So 1 over that,
Is
I'm making a point here.
3.81 times 10 to the negative 7.
All right, meters. My point is this. This is 2 microns. That is 38 microns. This is 0.38 microns. It's much, much less. The skin depth is much, much less than the thickness. Do y'all follow me on this? This is real important. So if the skin depth is much, much less than the shield thickness, the thing attenuates and you don't have to worry about multiple reflections. That's the point. Do you follow me, John? All right? This is real important. Now, if the skin depth was larger than the thickness of the shield, for instance, then you really should do the one I did where I showed you the transmission line approximation. Remember that? Then you need to do that kind of an analysis, which is a pain. This is much easier, thank God. Any reasonable shield would be very thick unless weight is an issue, like when they're launching probes in space. And then they will do things where multiple reflections will kill it. So just remember that there are other factors, but nothing significant. Okay, now back to this thing. I want this transmitted field's magnitude. So I know I take the incident field, whatever it is, then it's times the transmission coefficient's magnitude in region 1. Do you agree with that? Take a moment, right? Now I have to multiply it by the rate the magnitude goes down, which is e to the minus alpha d. You could take the magnitude of e to the minus gamma times d, because the imaginary component, the beta component, has no bearing on magnitude. Y'all with me? All right. Then I have to take the transmission coefficient in region 2, and that would give me this. But what is the transmission coefficient going from the shield? Let me put it here. Transmission coefficient from the shield into the second region. You remember how I told you to do it? You always say it's 2 times the impedance you're going into, eta naught, over the impedance you came from, right? Well, that right there, over the impedance you came from, eta shield plus the impedance you're going into, eta shield plus eta naught. Correct, class? Well, that is what? This is about 2. Now, if you want an exact calculation, you can get it, but it's not going to change your answers to any noticeable extent. Y'all with me? Everybody? Okay, so that's 2. So I come over here. Now I have eta 1, I have this, and I have this. I calculate eta naught. The incident field, the electric field's magnitude, the incident field's magnitude. And that's going to be E transmitted, the actual transmitted field that I give you, and simply divided by all this stuff. Magnitude of tau 1, magnitude of tau 2, times e to the minus alpha d. And can you give me that magnitude, please? Anyone?
I got 10.016.
And that should be volts per meter, correct, class? Y'all with me? And make sure, I don't know, there are all sorts of crazy errors that I couldn't really figure out that happened during this, but it was meant to be straightforward. You're just reverse engineering this. Y'all with me, class? All right. I've got that. After that, everything else falls apart. Once I have the incident field strength, based on the forward process we did, what else do we need? And I'll put the next part here.
Reverse or reflection.
The reflected electric field magnitude. All right. Well, it's about the same, isn't it, class?
Yeah.
I didn't even put down the reflection coefficient, but what is it? Isn't it approximately -1? It's not quite. What is the actual value for the reflection coefficient?
Negative 0.996.
At what angle? No, how about 0.96 at what angle? It's gonna.
I had like 0.009. So I
That's
just
reflection, not transfer.
Oh.
Reflection.
I just kept mine in rectangle.
All right. What did you get in rectangle? Just give me. reflection.
0.9976 or negative 0.9976
Minus 0.9976, go ahead.
plus J of 0.002.
So it's almost minus 1. Agreed? All right, that means the electric field strength reflected, I'll put it right here. If that's incident, I'll put it there. If that's incident reflected field strength magnitude is really, it's that simple. It's just magnitude, the reflection coefficient, times magnitude, the incident field. And what's that? Almost 10, but what do you get? Minus, or plus, I'm sorry, 9 point what?
993.
Almost the same. I was very lenient on this one. Y'all with me, class? I mean, if this is 99% of that or vice versa, you got it right. Now, what's the next part?
Real quick, could you have used the equation just like incident plus reflected equals transmitted?
Yeah,
to
but
do it?
again, the issue is always how many significant figures you have here and here. So that's the only thing I caution you on. Yes, mathematically, it's absolutely correct. All right, back to this thing. What's the next thing I'm asking for?
Power density of the transmitted wave.
This is the one where you have to be careful, and I try to caution you about that. First, I'm going to get the transmitted electric field magnitude, right? And so I found out that the transmitted electric field magnitude, we're going to get that. I'll call it E transmitted in region 1. It's right as it gets back through the interface. It's just magnitude of tau 1, the transmission coefficient, times magnitude of the incident electric field strength, right? Please watch this. This is where errors were made. I think some people got everything right but this one. Y'all with me? So now, when I take a look at that, we got the magnitude of tau 1. Well, here's tau 1. It's 0.00338 roughly. Times the, what do you get for that value? Or I'll tell you what, leave it like this for now. Do me a favor. I just want to leave it like this. That's the transmitted electric field just after you enter the shield. So it would be like if you're coming in from air and you're just on the other side of this boundary, that would be the value of the electric field. Can everybody follow me on this? You can put it at z equals 0 here if you want. Let the interface be at 0, 0 for this one. Now at that point, now you have to say the average power density. You're going to be tested on this again. The actual average power density right there, and this is just after, on the other side of the shield, and I'll call PF transmitted right here. That's going to be 1/2 the magnitude of E transmitted in region 1 squared over the magnitude of the shield impedance. Does everybody understand it? That's the first part, right? Now, normally there's an e to the minus 2 alpha z, but we just want it at z equals 0, just as it gets to the other side. Y'all agree with this? And then you're going to have cosine, and this is the part you got to watch for, cosine of the angle associated with the shield's characteristic impedance or intrinsic impedance. Right? Agreed, everyone? I'm going to remember that. This is what you got to, this is one do you remember me going over this? I made a big stink about this. You have to know this one. That cosine business comes in. So this is going to be equal to what? We got the transmit, you got the magnitude. Cosine is cosine of 45, agreed class? It's 1 over square root of 2. What do you get?
I got, so the first one you asked for was just the transmitted wave out of the shield, and then you asked for it right
What?
as,
Say again?
so
The first what?
the first question you asked about power density was for the transmitted wave, like as it exits the shield.
Okay, I'm sorry. This is just, this is
But that's the next question.
well, we'll do, all right. What's the power density he's asking? Once the thing gets out, we're in air, correct, class? So this was the next question in the order that appeared. So if we have the actual power density and we're in air, or it's outside the shield on the other side, it's simply 1/2 magnitude, and this is the field I gave you, right? Transmitted region 2 squared over, in this case, it's just 120 pi. Do you agree with that, everyone? That, because now you're just simply taking the numbers. Everything's given except for that formula, and you put it together and you don't have to calculate. And what do you get for this value? I'm sorry.
I got 1.69 times 10 to the negative 10.
watts per meter squared. With me? I think that's the answer in the solutions, roughly, right? Again, it's in air. There's no cosine of an angle you have to worry about. Getting back to this though, thank you for reminding me. What's this gonna be? Now you've got cosine 45 degrees and eta shield is almost nothing. 0.639, right? So what do you get for this one?
6.34 times 10 to the negative 4.
Y'all agree with that? Now, here's something you need to be aware of. Everybody listen. Almost. Anyway, everybody, if you listen to me, what if I asked for, suppose this is the shield thickness, this is the thickness D. Suppose I wanted the power density at D over 2 into the shield. Got me on this? Everybody? How would you get it? You tell me. You know the power density here, don't you? What do you know I have to do to expand that formula? I just need to put the e to the minus 2 alpha z, right? And that z would be d over 2. Y'all with me? I'm going to understand that. Bradley, Andrew, you with me on that? So be aware of a question like that appearing on a test, on a final exam, or somewhere in a quiz. Got it? You're going to see it again, at least once. Because that's one where now you simply take this quantity, and if I call that just PFT right there, and if I wanted the actual value of the power density anywhere in the shield, you could say the average power density anywhere in the shield is a function of D. This would be in the shield. Would be equal to that power density, I'm just calling it PAV, and looking at the best notation, T times e to the minus 2 alpha, and then the position z, and z would be the depth into the shield. Now one thing you're going to find out for yourself, but if this is the shield, this is the z direction, let's call this z equals 0. If you look in here, in this shield, the electric field's value right here on this side is only 1/2 the electric field that gets out. You all with me? But the power density in here is much higher before it gets out, because there is a reflector. And the reason it is because the intrinsic impedance of the shield is so low. And remember, power density is 1/2 E squared over the magnitude of eta. The magnitude of the shield impedance is 2 orders, 3 orders of magnitude less than the impedance of free space. And that's the reason the power density just before it hits is greater than when it leaves, and when it leaves, the power density goes down, but the electric field's value goes up because the intrinsic impedance is much greater. Can everybody appreciate that reasoning? So what I might do is ask you for the power density right here, or right in the middle, and the power density on this side. Just be aware of that. I want to make sure everybody's clear on that. Y'all with me? All right, what else is that?
Just phase velocity and skin depth.
Yeah, this is just sort of a gimme thing that you've got to keep these things in your mind all the time. I wasn't trying to trick you or anything. So in the shield itself, the real thing is anytime you want phase velocity, it's omega over beta. What else? Wavelength?
Just skin depth.
All right, well, we got the skin depth, right? So phase velocity, beta is alpha, isn't it, class? Or I should say alpha here, right? Omega is 2 pi f, so it's 2 pi times 3 times 10 to the 8th, because that's the frequency is 3 times 10 to the 8th. It's cycles per second, or hertz. Beta is equal to alpha is 2.62 times 10 to the 6th. And what is this? I don't even know. It's not the speed of light.
719.
Very low. That number probably bothers somebody. Meters per second approximately, correct? And the skin depth we got. Was there anything else I asked? All right. Whatever you did, mistakes you made, please just learn from them. Appreciate how you've made a mistake. I mean, I made some mistakes this morning just because I was stupid, my brain wasn't working. You may have had that same experience. the one thing I'll tell you is learn from it, and anything you don't know, force yourself to really learn before we go on, because you're gonna need it. This stuff does build. Now, I was doing oblique incidents last time. Y'all remember that? Yeah. And I gave you a problem. You with me? Y'all remember that problem? Did you do it? It wasn't a hard problem. It just makes you a little more familiar with those formulas. I'll give you the reflection and transmission coefficients for TE or TM modes. I'll put them up there for, we were doing TE, we can do TM too, but let me take a moment and erase all this stuff. Hey, I want to tell you one other thing before I continue. I looked at the calendar, actually this morning somebody reminded me. We have Juneteenth off, which I believe is June 19th. That's a Wednesday. We also have Friday off, and we also have Monday off because it's the end of the mini-mester. Do y'all understand that? That means we got a full week off from the June 19th is off, really from that Monday. We're not going to meet again for over a week until the following Wednesday. Y'all hear me? That is a heck of a long time. Please don't get stale. I'd keep up with this. I'll give you some stuff at least I encourage you to do. But that is a phenomenally long time in the summer because we got July 4th holiday coming up after that. And people are asking for the Friday off. Thinking, really? We came up with this calendar. Well, it's not my call. And I know so many students have a test Friday on thermal, or in thermal, pardon me. Look, there's still going to be a quiz, right? But the fact is this, if you keep up with it, you're not going to have to cram Thursday. The only thing you're going to do is sort of revisit some of the ideas, because this stuff all builds. So here's oblique incidence again. And this is for TE. Let me just get through this. So if we have region 1, region 2, and here I'm not going to use the index of refraction. I am going to use the intrinsic impedance because it's the way it's written in Whitmer's book. So in region 1, it's going to be equal to the square root. And this is all going to be lossless. We could do lossy, but it would be a little more difficult. A to 1 is just a... No, I'll just leave it as A to 1. You know the formula. And this is A to 2. I'm using this as lossy because if we do the lossless case, it's going to get mathematically a little more tedious. And this is the one that's typically done. In Whitmer's book, he does this. So then we have an incident angle, right? We have some theta incident. And we have an electric field. This is the TE case again. An electric field coming out of the board and a magnetic field in the board. And this is H incident here. We're going to have a transmitted electric field here, E transmitted, and the H field is in this direction, H transmitted. And then you're going to have the angle of transmission. You're going to have an angle of reflection right here. And you're going to have an electric field magnitude reflected. And you're going to have an H field. And the H field is in this direction. This is a picture in Whitmer's book. Do you have your books? They are available either online or you have hard copies, right? So this is T. Now, I put down the equations for all these things. I'm going to show you the type of problem I might give. In the incident field, I almost feel like referencing the book, but if you have the incident field here is going to be some E naught incident, and then it's going to be e to the minus j, and it's beta in region 1, right? And then it's going to be x, and here it's going to be times the sine of theta incident plus z cosine of theta incident, and it's in the A, in the way I'm doing it the way the book does it, AX direction. So this is assumed the X direction, and this is assumed the Z direction. And this is in his book. Can you give me the page number or figure number? just want to give you a reference to right now. I did it on Friday.
361.
361? So it's page 3, which figure number?
Figure 6.21.
6.21, page 361. Okay. That's the incident electric field. The transmitted electric field is equal to E naught incident times the transmission coefficient. Now, I'm putting in the transmission coefficient here because it would make sense. We've already figured that out. Do you all remember? And I'll put it down in a second. Then it's going to be e to the minus j, and here it's beta 2, and then it's going to be x. Now, I think he multiplies this sometimes, but sometimes he doesn't. It's going to be x times the sine of theta transmitted plus z times cosine of theta transmitted, and it's going to be the ax direction. Right? And then you're going to get E reflected, and that's equal to E naught incident times the reflection coefficient, and this is the T reflection coefficient, by the way, times E to the, and you got to be careful on the sign here, E to the minus j, it's going to be beta 1, but it'll be x times the sine of theta incident, or reflected, plus z cosine of theta reflected, or sorry, minus z cosine of theta reflected, AX. And, let me just put this up here. The transmission coefficient is equal to 1 plus the reflection coefficient. And this is let me put the reflection coefficient down first for the TE mode. And I know a lot of you are writing this down, but I'm going to say something. This is the way I always do these problems. I know the reflection coefficient always has a general formula. You're going to have the impedance you're going into minus the impedance you came from over the impedance you're going into plus the impedance you came from. But there's going to be weights next to them. And the weights are cosines. You with me? So this, because it's T, I know it's beta 2, and it's cosine here of the incident angle. Take a look and confirm that. And this is going to be cosine of the transmitted angle. We proved this. This is going to be cosine of the incident angle, and this is going to be cosine of the transmitted angle. Do you see that in the book, by the way? Give it a moment to take it. And then the transmission coefficient is going to be 2 times theta 2 cosine of theta incident over theta 2 cosine of theta incident plus theta 1 times the cosine of theta transmitted. Take a moment. You see these in the book, by the way? I want to make sure he gives me a page. Give me a page number, and I mean they're going to have this. They're going to have EI equals, or E reflected equals E naught I. Which one's that?
Page 367. They've got the they've got that's 6.141 of sorts.
141,
Yes, sir.
and this would be 6.140.
2.
Oh, is it 6.142? Somewhere in this equation.
Or they might be vice versa.
It doesn't matter. They'll figure it out. Got me on this, class? Now, I would give you this. This is TE. But if I gave you a problem, let me just show you what I'm talking about. If I say I have an electric field of 12 volts per meter out of the board propagating at a certain angle, say theta equals 45 degrees. You all with me? In a region 1. I would give you something like that, magnitude, angle, or something of that nature. From that, I might ask you for the angle of transmission, which we'll get in a second. I might ask you for the transmission coefficient, for the transmitted electric field strength, you all follow me? Or the reflected field strength, or the reflection coefficient, or any of the like. Or I might ask you for the magnetic field's magnitude. Now, the nice thing about this, it is lossless. You all with me? So if you have the electric field strength in any of these regions, and you want the associated magnetic field strength, you simply divide by the intrinsic impedance of the region. Y'all hear me? Y'all know it? I'm talking, if I'm magnitude-wise. I'm not gonna ask you for the equations for the magnetic field. They're a little tedious, aren't they? There's gonna be, these have all what? Just one directional coefficient. I mean, it's only gonna be polarized in the AX direction for TE. The H field will have two components, right? Y'all with me? So I might even give you these equations and maybe the H field equations. But if I gave you a problem, and here's what I've done in the past. If I say this is air, no, this is the kind of problem I gave you. Right? I gave you a problem just like this. If you didn't do it, please do it. But try to work through it without looking at the solutions. And this is in some region where we're going to have air, call this A to 1 equal to A to 9. And over here we're going to have A to 2, but it's lossless region. And suppose I give you something like this. I give you a drawing. And I say the values for A to 2, assume you have that. And I say that the transmitted angle is like 13 degrees. And the electric field strength of the transmitted field is 10 volts per meter. Got me on this? So I'm giving you information about magnitude and transmitted angle of the transmitted electric field. And I want to know the value of the incident electric field. You should be able to get that. That's the inverse problem, isn't it, class? You know the incident field times the transmission coefficient would be the strength of the transmit field. So that checks the box. You should be able to back engineer the incident field strength, right? What law do I use to get the incident angle here?
Snell's.
That's right. If you want the incident angle, what is it? You're right. Okay, go ahead. How many remember Snell's law? Don't just cram for it. Learn it. You're going to need this. The way I say it to do it is beta 1 sine of theta incident is beta 2 sine of theta transmitted. Now, that's the general form that's true for a lossless medium. The nice thing is, because it's lossless, beta is just omega squared of mu epsilon. Do you all agree with that? You know what I'm talking about?
Yeah.
Everybody? If it's lossless, alpha is 0, beta is simply omega squared of mu epsilon. Then take it from here. People mess this up. So it's going to be omega square root of mu naught epsilon naught times square root of mu relative epsilon relative times the sine of theta incident is equal to omega square root of mu naught epsilon naught times square root of, and this is, I better call it mu relative 1, mu relative 2, epsilon relative 2, and then it's going to be the sine of theta transmitted. Now, I'm writing it down one more time. Y'all with me? No Snell's law from that form, and make sure you understand what beta means. So if you take a look at this, does everybody see the omega cancels on both sides? Can y'all see it? All right, so I'm just getting rid of omega. I'm sorry about my writing. I'm trying to write better. Now, the reason I always break out the square root of mu naught epsilon naught, because it always appears on either side, right? That's just 1 over the speed of light, so get rid of it. Now, usually, it's non-magnetic. Matter of fact, I don't think I've ever given a problem with Snell's law where I've had a mu relative other than 1. There's always a first, but not in this class, graduate class. All right, so get rid of that. Now, do you remember what we call the square root of epsilon relative? And y'all had physics, y'all had optics. Remember what they called it? It was the index of refraction, right? Index of refraction. Y'all with me, class? Do you remember that? This is real important. You remember the classic example I gave you from light goes into water, electromagnetic, and it bends sharper in the second region. It will always bend to what they usually term, I don't like this, but they call it the more dense medium. So anytime you have something where the index of refraction is larger it's called a more dense medium. It just means the velocity of light is slower, that's all it means. So if you go and you've got 45 degrees here and you're going from air to water, this angle is going to be a lot less, guaranteed. It'll bend towards the normal. Right? And as this one, as the index of refraction approaches infinity, it'll come and go straight like that. Just remember that, always bends towards the normal. So if you're looking and you're going to shoot something underwater and you're at, say, 45 degrees to the normal, your arrow is going to look like it broke and going straight down, because that's the way the light is actually coming back at you. It's hitting there and reflecting. So you always aim under the object. Has anybody ever done anything like that? Stabbed something underwater, shot a bow? I don't think I've ever shot a bow in water, but I shot a pellet gun once. So that's the way you have to view this problem. Okay? I'll tell you one other thing too, and I'm not going to harp on this. If you have a normally incident wave coming in here, then the incident normal, that means 90 degrees, it's coming right normal at that. Then the incident power minus the reflected power will be the transmitted power density, I should say power density. But when you have an electromagnetic field coming like this, where it's at an odd angle, it's not incident minus reflected power density, it's transmitted. Here's why. See this angle being different? So the actual power is flowing this way, hitting, the reflected power is going this way, the transmitted is going this way. If you take the component of power that is normal over here, so the power density normally incident, say you get the incident wave here, it's got a certain power density. Take that power density and multiply it by cosine theta, that would be the normal power density. And then subtract off of it the reflected power density times the cosine that angle. By the way, I didn't mention this, but the reflected and the incident angle are identical. Did you remember me saying this? How many have played pool or billiards, whatever you call it? I mean, I used to play pool. And one thing that is generally acceptable is the angle, if you have a normal, and this is a bumper, the angle you come in and hit it at will be the approximate angle it reflects off. Right? Angle of incidence is equal to angle of reflection, always, for any electromagnetic event where there's a planar surface. And I have to say, it's all right. How many have played pool in here, billiards? How many know there's something called English? All right. Well, it's spin on a ball. Yeah. You can do crazy stuff. I'm talking about the general sense. Okay? Just a thought that occurred to me, and I'm thinking, I know somebody's going to come at me. All right, so you have to take the component of the power density that's normally incident, watts per meter squared. On one side is equal to the power density on the other side of the normally incident wave. Got that? That's important. There's a lot of weird things that happens when you have, there's something, this is going out. Anybody in here interested in graduate school? I'm going to encourage you about one thing. If you're good students, I cannot tell you how much of a benefit it is to go to graduate school. You have no earthly idea at this point in your career. You think you're just out to make money. It was that way for me too. I was thinking that until a professor would talk to me and said, I mean, not everybody can do it, but if you're smart and stuff like this, graduate school opens so many different paths and doors, and it's your career. Assuming you like what you're doing. Some people hate this, they're doing it for the money and they can't wait to get into sales when they get out of here. But if you like what you're doing, want to do it, think about graduate school, come talk to me, I'll help you. You cannot imagine the benefits it has, and it's paid for. If you're a U.S. citizen, and if you're a foreign national, they usually have support mechanisms. I'm just leveling with all of you that there's absolutely, it's an incredible opportunity, and I can't believe more people aren't beating the path to get into graduate school because of so many benefits. And grad school's fun. Compared to undergraduate, it was like, I never had enough time to get the work done I was given. And I went through school in 3 years. Am I over? I'm not over, am I? Oh, sure. Whenever I have people looking at their phones like that, I'm just worried. All right, please consider, just consider. You'll not regret it. I mean, the only person only time I've ever heard of anybody, I've never heard of any medical doctor, lawyer, engineer, vet, anybody that went and got a PhD or the equivalent medical degree or vet degree, ever regret, the one minor case might have been an art history doctor, which is not really a marketable item. I mean, maybe it is some other countries, but you don't see people beating down the doors looking for art history people that just talk about art history. Anyway, that's about the only thing I'm going to tell you about grad school, but I do want to make a pitch about that now. So please consider it. Back to this stuff. This is all TE. We're going to do TM, and I'm going to do it kind of quickly, but there's one thing about TM mode that's real important. It's called Brewster's angle. And that's where nothing is reflected and everything gets through, even though the media have a different values of eta, which doesn't make sense, does it?
I'm just saying what TE stands for. One more time.
Transverse electric. Well, I mean, can anybody tell them in their own words that these are two media, right? Transverse electric, the electric field is perpendicular to the plane it's propagating in. But the way I always think of it is, think of this boundary between these two layers, right? Think of like, if that is the earth and this is the air. If you have, and this is the way it is in radar, if the electric field is parallel to the Earth's surface is in the XY plane. If the electric field is this way, if it's parallel to it, or it's horizontally polarized, that's TE. With radar, it's really easy, because that's the thing we always think. If it is perpendicular, all right, if the electric field, I mean, if it's, this is parallel to the plane of separation, right? Now, if the electric field was in the plane, suppose the electric field is going to be, let's say the magnetic field is out, this is what I'm about to do. Then, if the magnetic field was in this direction, that's called TM, transverse magnetic. It's just like transverse electric, only the magnetic field is sticking out. And we're about to do the transverse magnetic thing. This is important because it has a very unusual property. That's Brewster's angle. You don't remember the name Brewster's angle from physics? Some of you do. Last time, did I do the thing with sunglasses or get somebody to polarize sunglasses?
Yeah.
Do you have polarized sunglasses in? Remind me, after I do Brewster's, we're gonna. You got a pair?
No, I was saying.
You got a pair. Anybody else got polarized sunglasses here? You might.
Yeah, I think they're polarized. Actually, I don't know.
I mean, this is how you can tell if they're polarized or not. Huh?
Yeah, we'll figure it out.
Did anybody look at the eclipse that happened earlier this year? All right, now, we had eclipse glasses, but you could actually take two polarized glasses and get it to the point, move it to the point where it's almost dark. You know what I'm talking about or not? Might as well. I almost want to have fun like this now. First, let me put up the TE stuff, because this is one thing I want to get done. Then we'll have fun. So TM mode. So we did TE, right? So for TM mode, TM propagation. All right, we have region 1 and we have region 2. I'll call this eta 1. Now remember, these are intrinsic impedance in eta 2. They are not the index of refraction. Index of refraction is an N, but this is meant to be a Greek letter eta, even though my writing doesn't do it justice. And here we're going to do the same as we did before. This is the Z direction. This is the X direction. And we start with the incident field, but this time it's magnetic. And here, now we're going to have an incident magnetic field that's sticking out of the board. Let's see if I can do this with different colors. Finally starting to wake up a little. I don't know what happened. So I'm going to call this the magnetic field, and it's H incident magnetic. It is out of the board. You all with me? If you think about it, that means the E field has to be into the board like such, right? Because E cross H would be the direction of propagation. Does everybody follow me on this? Are you with me? That would be this is the incident field. It's in the plane of propagation. That's the H field sticking out of the board. It's going to give rise to, and this is at some incident angle. Here, you're going to have an H field that's out of the board that is transmitted, and you're going to have an E field in the plane of the board that's transmitted. And you're also going to have a reflected field. Now, the angle of reflection is all, and this is going to be an angle of transmission. The angle of reflection is always going to be the same as the angle of incidence. And here, this is a crazy one. Here in his book, he's assuming the H field is in the plane of the board. And I want the page number on this one, and I want to give you a reference for the figure, because this is a little confusing. And the reason is that the reflection coefficients always have to do with the ratio of the electric fields. Just trust me on this one for now. Never the ratio of magnetic fields. Say again?
366.
Okay,
There's that diagram.
thank you. Yeah, that's it. And if you look on page 366, it's figure 6.23, you'll see he'll have the magnetic field going into the board on the reflective field. So this is going to have a cross on it. Let me mention a few other things. The E field, if that's going into the board, that means the electric field would be in this direction. E reflected would be in this direction. Can you all follow me? Because E cross H is the direction of propagation. Now, this is important. Most of you probably know this. The reason they do this dot or cross, the cross, think of an arrow when fired from a bow. If it goes into the target and you see feathers, it's going that way, right? Here's feathers, it's going in. If you see a dot, it's coming at you. That's the real way it was explained to me. It makes perfect sense. See a dot coming at you first, that's coming at you. So that's the dot versus cross convention. If you take a look at this, I could write the equations and I could go ahead and match boundaries as before, correct, class? And that's what he does. If we do this, this is what we get. You all remember me doing that on the board for TE? We can do it for TM too. A couple of interesting things though. I'm going to put up one thing, and you can tell me which. The incident field, he's not going to call it H naught incident. He's going to say it's going to be E naught incident over eta in region 1. Do you see that? And then he's going to have this as e to the minus j beta in region 1. This will be the same as it is for TE. And this is TM mode. And here he's going to have x times the sine of the incident angle plus z cosine of the incident angle. And he's going to have AX. Can you all see that full? Can you see it?
Use AY.
Oh, I'm sorry. I'm so sorry. This is out of the board. I'm sorry. That's X, that's Z, this is out of the board. So it is a Y. I'm very sorry about that. You're absolutely right. It's perpendicular. You know what? For the TE mode, the E field is AY as well. Because he's got AY coming out of the board. Do you all see that in the book? The reflection and transmission coefficients are the same, but I think I put the wrong coefficient up for when I put in the TE mode. Was that right? Was it AX I put there instead of AY? I'll correct it right now. Do you have it down, Keenan, or not? Go back to TE and just see. I'm sorry.
Sorry for what?
I want to see if the coefficient was AX or AY. It should be AY. It is AY? Thank God. Got something like that. All right, this should be AY, and it should be amps per meter. But you'll notice it does not have H naught. H naught is the H naught incident. H naught incident is the ratio of E naught incident over eta. Now the reason he's doing this is when he defines transmission and reflection coefficients, it's always ratio of transmitted E field to incident, not transmitted magnetic. Y'all follow me? So transmitted magnetic field's ratio to incident E field is not the same as transmitted E field to incident E field. They're different because the eta values affect it differently. So that's the incident electric field. There'll be a transmitted electric field and a reflected, this is the incident magnetic field. There'll be a transmitted magnetic field and a reflected magnetic field. At the end of the day, the incident electric field I'll put it reflected electric field over the incident field. Now this is going to be the reflection coefficient for Tm, but that'll be equal to eta 2, and I always start eta 1, eta 2, eta 1, and here it's not going to be cosine of theta incident, here it's going to be cosine of theta transmitted, minus eta 1 cosine of theta incident. This is going to be cosine of theta transmitted plus cosine right here of theta incident. Now, do you see this formula? Or he'll have the ratio, I think he'll have E reflected equals E incident times this. What formula or what equation is that?
Those were the ones I told you earlier, the 6.141 and 6.142.
Yeah.
I got them, the
ones-
TM.
These are
ones
TM.
Yeah.
The ones for T were earlier.
All right, I'm sorry.
Yeah, that's fine.
That's a, but this is 6 point,
141.
all right, in that area. So that's reflection. Now the transmission coefficient isn't 1 plus that. That's the important thing. It's not. So the transmission coefficient for Tm, and this is the weird one. Usually you just take twice that first term up top, not anymore. This one is going to be 2 times eta 2, but then it's going to be cosine of theta incident. You're going to have to confirm this. I don't trust myself anymore. Eta 2 cosine of theta transmitted, cosine theta transmitted plus eta 1 cosine theta incident. Now, you got your book open, it looks like. I want you to notice one thing. Can you see this for transmission coefficient? It's 2 eta 2, and there's a cosine of theta incident here. You see that? All right, and then it's down here is eta 2 cosine of theta transmitted. Can you see that? And this is going to be cosine. So this is different. Now, in any situation, I would always give you these. I don't expect you to memorize these. It's just, I've worked with this stuff a lot in my life, and that's the only reason I just feel comfortable talking about it. And even now, when you're tired, you can make mistakes. So this is something that's really important. And it means that this is not equal to 1, this is not equal to 1 plus this. That's real important. Y'all with me? He'll even have a formula where it's going to be this plus 1 times a cosine ratio.
Yeah.
But I just don't even bother with that. I just have these, okay? For Tm. So if you know the incident field, you know the reflected field. Now here's the kicker. And this is only true for Tm polarization. You can get a reflection coefficient of 0. Got me on this? That means everything is transmitted. And I want you to watch this. Set the reflection coefficient of the magnetic field, or really transmission coefficient equal to 0 of, reflection coefficient equal to 0. Now watch what happens. I'm going to talk my way through. Don't mess with this. All right? Don't worry about this right here, because setting the transmission coefficient equal to 1 does not imply everything got through and nothing is reflected. This has to do with the ratio of electric fields. Remember, it's the H field that's perpendicular, not the E field. It's real important to just listen to me for a second. So when I set this equal to 0, can you all see what I'm doing here? I'm saying there's going to be a point when the reflection coefficient is 0. Here's the reflection coefficient. You all see that? I need your attention for this part. So if it's equal to 0, this bottom part doesn't matter. So now I can say what that implies is eta 2 cosine, and this is theta transmitted, plus eta 1 cosine of theta incident equals 0, correct? I'm sorry, minus this equals 0. I'm sorry, minus that. In other words, this top part I'm going to set to 0. Here, I can do this. I can take either one of those to the other side and I get this equation, right? Now, there will be a unique angle called the Brewster's angle. And Brewster's angle always has to do with an angle of incidence. This is region 1 and this is region 2. We're coming in at a certain angle of incidence. When the angle of incidence equals the Brewster angle, everything is transmitted, or this is true. Follow me? So Brewster's angle right here, I would say that eta 2 cosine of the Brewster angle is equal to eta 1 cosine of, this is transmitted angles, cosine incident times theta of the Brewster angle. Now we're going to go ahead and figure out what the Brewster angle is, but we're going to use Snell's law to get it. He does it this way. So bear with me. I know it's a little boring for some of you, but hang with me around here for a second. I'm going to show you a trick that hopefully will help you later in some of your courses. These are things you learn over time. So I know that I said, let me do this too. I'm going to assume it's a lossless regions, and I'm going to assume non-magnetic. Because this is the big deal. Most of the time when you're doing these kind of problems, they're really optics related more so. All right, it is true at lower frequencies this works, but we don't worry about magnetic materials and we don't worry about lossy materials when we do this. Or then it's a completely different game when it's lossy, especially. So if we have this, if you remember what Snell's law would be, it's going to be square root epsilon relative 1 times the sine of the incident angle is equal to square root of epsilon relative 2 times the sine of the transmitted angle from Snell's law, if it's lossless and non-magnetic. Does everybody agree with that part? Can you all see? All right, if that's the case, I'm going to do something I think everybody understands. I'm going to square both sides. So I have epsilon relative 1 times the sine squared of the incident angle is equal to epsilon relative 2 times sine squared of the transmitted angle. Okay. Now remember, that sine squared business is, if the incident and transmitted, I can make them 1 minus cosine squared, right? So I can go ahead and I can say I have epsilon relative 1, and I can have 1 minus cosine squared of the incident angle is equal to epsilon relative 2 times 1 minus cosine squared of the transmitted angle. Now, I have reflected cosine squared of incident and cosine squared of reflected. I have cosine of incident and reflected here. I called it the incident angle Brewster's. Tell you what, I'm going to leave it as incident because this would be the point. I want that angle. And when I take a look at this, I'm going to solve for cosine of theta transmitted. Just watch. I do that, I take this and I divide by epsilon relative 1, or epsilon relative 2, pardon me. Now I have this. Can you all follow me? I have that, and then what I'm going to do if you take a look at this, because I want that cosine squared business, if I take this, and I can make it minus, makes that minus, makes that plus, take that to the other side, take the 1 to the other side, and then take the square root. Well, it's a long, driven out thing. So I can say that cosine of the transmitted angle is equal to this. Now, this will be the Brewster angle, because I've set those two equal to each other. Can you all follow me? This is the angle I solve for. It gets a little messy here, but follow me. If you know epsilon rep, I've got 1 minus this, and I have 1 minus the cosine squared. If you want to, you can leave it as simply being sine squared there. You all with me? Doesn't matter, but when you get to this point, you can take this cosine of the transmitted angle here, stick it in here, and then you have one equation with one unknown. Now, in his book, and I know I'm getting out of time, in his book, what he does, he's going to show you what I put up there, but he goes through and he has one crazy equation on an equation 6.146. If you take a look, it's on page 367. It's kind of a whole bunch of beta squared, zeta squared business. Can you all see that? It's equation 6.146. 99% of the time, nobody cares about magnetic materials. So if you turn the page, in equation 6.147, here's what happens when it's non-magnetic. It's just the sine of the Brewster's angle is equal to square root of 1 over 1 plus epsilon relative 1 over epsilon relative 2. You see that? I would give you that equation. But I want you to know the reason that's so important, everything's transmitted at the Brewster angle. Nothing's reflected. That means no reflected power. Now, it's very odd because what did you notice? Two different materials. If it's normally incident, I have a reflected wave. But at the Brewster's angle, everything's transmitted. That is counterintuitive unless you go through it. Who else has polarized sunglasses? I know you do. Anybody else in there? Andrew? Nobody? Just one person? This is summer. Are you serious? Not even you? Are they polarized?
We don't have any.
We're gonna find out. I don't have time to go through them. Yeah, that's right. So these are filters. Now, I don't know if it's gonna make sense, but if you look, if they are polarized, how about we do it this way? I can see you, but you can see, I can't see. Can you see that? Just look at me.
My glasses are like reflected on the other end, so like you can't, you just see yourself.
Well, oh yeah, oh god. Anyway, if you do this, if I took a flashlight on this side and I get them at 90 degrees, they're perfect filters. We're going to talk about filtering and how that works later. Wait, that's yours, sorry. Anyway, pretty sorry about that. But we'll talk about some of the implications of this stuff and filtering and Brewster's angle and everything transmitted, because it's used all the time. That is a Brewster's angle. I'm just showing you. Okay, I think is my time up?
Yeah.
Yeah.
Seems that way. It is now, right? I'm done. Thank you for doing that.
It looks like there's some